color? What makes color, and how does the eye detect the wavelengths that we interpret as the colors of the rainbow? The electromagnetic spectrum is very broad, but of course, we really like the things that center around us. And so that bit of the electromagnetic spectrum that we can see, the visible, that's what we think of very often as the most important part. It's a small fraction of all electromagnetic radiation, but it's very important for us in how we interact with the world. If we take a look at the solar blackbody radiation spectrum, we'll see that when the radiant energy density is plotted versus wavelength, it peaks in the green, and that's right where our eye is most sensitive. Of course, that's not actually where the most photons come out. If you plot versus frequency, the picture looks much different, and indeed if we plot the number of photons versus frequency, we would see that that peaks far out in the infrared. But of course, photon energy and number are both important for determining what we see. And this region is, for whatever reason, what humans are most attuned to. Other animals can see further into the infrared or the ultraviolet, but we see the colors of the rainbow from red to indigo. There are 15 distinct sources of color production. Some of them rely purely on geometrical and physical optics. For instance, we've already talked about why the sky is blue. That's Rayleigh scattering, elastic scattering of photons that would have missed the Earth, but then get knocked down into our atmosphere, and we see them then as the blue of the sky. The clouds that you see here are white. White and black sort of aren't really colors. White is when we see all wavelengths of light together, and black is when we don't see any of the wavelengths. Why are clouds white? Well, clouds are made up of water droplets. The water droplets are comparable to the wavelengths of light, and they scatter all of those wavelengths equally. Since all of the wavelengths that hit the clouds are scattered down toward us, we see them as white. But of course, these mountaintops, volcanic mountaintops here, that lava rock is absorbing all of that light and therefore looks black. The white of the clouds, that's created through a scattering process known as scattering, this size-dependent scattering. Another way for scattering to make an object look black is take a semiconductor like silicon. If you have a polished surface, it would be nice and silvery. But if we structure it such that, by putting pillars on it in this case, such that those pillars would scatter the light forward rather than back at us, since silicon is an absorbing material, that region that has been topographically changed will appear black because it absorbs all of the light. Of course, another form of physical optics creating color is that of refraction. Again, small water droplets here, but this is an angle dependent and size of the particle dependent phenomenon to get that refraction. And then if we're at the right angle, if the source, the sun, is at the right angle and you, the detector, is at the right angle, we will see the white light scattered into different angles based on its wavelength, and that's what leads to the colors of the rainbow. Structural color is widely observed in a number of materials and in nature. Sometimes we'll see structural color. Structural color is when interference or reflectivity effects are wavelength dependent, and then based on the optical path difference from waves that come in and hit the top of the surface and go through to the bottom. In this case, we have a porous film with a different refractive index than the material below it, and so there's slightly different reflectivity at the top of the film and the bottom of the film. And when those waves recombine at our eye, we see different colors because of the interference effects in that film. You can also do that with a solid film on top of another solid. For instance, if you take silicon and put it in an oven, you can make SiO2 layers of different thicknesses, and the different thicknesses have different colors. This phenomenon is also what gives blueberries their blue color. Blueberries actually have a red pigment in them, but a waxy coating on the outside changes the reflectivity spectrum, again through this structural interference color effect. And the reflectivity maximum is out in the blue to UV, therefore we see them as blue. This is also structural color. Imagine now you could actually change the optical path through your film, perhaps by putting a fluid in there and changing the spacing. This is how chameleons can change their color through variable structural color generation. Scattering is also at the heart of opalescence. When the scatterers have similar wavelengths, similar sizes to the wavelength of light, and you have a distribution of those sizes, you can get differential scattering of the different wavelengths, which leads to these fiery colors of fire opals. Different gemstones exhibit very different generation of color mechanisms. For instance, in amethyst, amethyst gets its color from color centers. What are those? Well, amethyst is composed of quartz, that is a crystalline form of silica, which would be clear if it were perfectly defect-free. However, defects introduced into the crystal lattice introduce electronic states into the band gap of silica, of quartz, crystalline silica. And transitions between those defect states leads to the color of amethyst. Meanwhile, other insulators, such as alumina, again, a perfect alumina crystal would be clear in the visible, but if you introduce metal impurities, such as chromium for ruby or iron and titanium in sapphire, then those metal ions introduce electronic states into the band gap of the insulator. Electronic transitions between those electronic states absorbs light. Remember, you don't see the absorbed light, you see the transmitted light. The complementary color to what was absorbed is what you see as the color of the object. Some materials are semiconductors. Fool's gold or iron pyrite is a semiconductor, and its band gap is just right such that it absorbs light well out toward the blue and it gets this golden color. Incandescence is the light that's generated from heat, such as when you have a combustion reaction or in flames, you can get hydrogen and oxygen to mix and they form a nice fireball, and incandescent light is seen from that. Light that comes from chemical reactions is also known as chemiluminescence, when the energy of the enthalpy release in a reaction is sufficient to create molecules in an electronic excited state that then can radiatively decay. Luminescence is light that we see from a solid object. In this case, porous silicon with very small crystallites, nanocrystallites, that have been excited by a black light. These are under black light illumination. In other words, ultraviolet light has been used to excite these solid structures electronically. And when the electron in the excited state, the conduction band, falls back to the valence band, it releases energy radiatively that we see as luminescence. So how does the eye differentiate between different wavelengths? How does the eye detect different colors? It all comes down to the properties of this molecule, 11-cis-retinylidene. That's the chromophore of human vision. You might have heard of the rods and cones that are in your eyes. Rods and cones detect light and somehow transduce the absorption of light into a signal that your brain interprets as the different colors. Rods act at low light levels, and cones are better at bright lights. Cones are also better for observing colors. In very low light conditions, you may have noticed your color perception is not as good. The rods aren't as good as that. The cones, on the other hand, are very good at color perception. Why? Well, this molecule, 11-cis-retinylidene, when it absorbs a photon, it undergoes an isomerization reaction. This isomerization reaction creates the trans state, which eventually relaxes back to the cis state. and waits around for another photon. When the reaction occurs, this isomerization occurs, that is transduced into an electrical signal that the brain interprets as, oh, a photon has come in to the eye, has been absorbed in the eye, and now I'm going to see that as a color. But how does one molecule lead to seeing many different colors? The answer is how a chromophore reacts to its chemical environment. And in the eye, opsins, these are proteins, 30 to 60 kilodalton proteins, that surround and encase the 11-cis retinylidene. And when the protein environment changes, it changes the absorption spectrum of our chromophore. Depending on which chromophore is excited and how intensely that chromophore is excited, that's how the brain interprets different wavelengths of light as different colors. And indeed, if you've ever heard of color blindness, what happens in that case is the colorblind individual does not have a full complement of all three protein environments around the chromophore. And true colorblind, in really extreme colorblindness, there's only one environment, and so you basically see gray, because the human brain needs the comparative excitation of these three different chromophores in order to get full color vision and see the colors of the rainbow.